Okay, so hi everyone. This is the sixth public Colloquium of Extreme Universe project, and this time we are extremely happy to have Professor Gary Horowitz from University of California, Santa Barbara. And let me briefly introduce him. He obtained his PhD from University of Chicago in 1979, and after spending some years as a postdoc at Oxford University, and also he was a member of the Institute for Advanced Study, Princeton. And then he joined the faculty in UC Santa Barbara in 1983. And he's been a member of the National Academy of Science since 2010, and he was the president of the International Society on General Relativity and Gravitation from 2013 to 2016, and chair of the Division of Gravitational Physics at American Physical Society from 2019 to 2020. And he's been recognized as world-leading experts of gravitational physics, both classical general relativity and quantum gravity and string theory. And in particular, he has been studying properties of space-time singularity and black hole from two-dimensional to higher dimensional. And today, he is going to tell us about space-time singularities and black holes. Okay, Gary, please start.
Okay, thank you, Akihiro, for that kind introduction. Well, I've been studying space-time singularities and black holes for most of my career, but this is a particularly appropriate time to tell you about them, not only because there's been theoretical and observational progress, but also the 2020 Nobel Prize in Physics was for black holes. Roger Penrose was recognized for his theoretical work, and Reinhard Genzel and Andrea Ghez were recognized for their observations of stars circling the supermassive black hole in the center of our galaxy. But despite what the Nobel Committee said, Roger Penrose did not prove that black holes are a robust prediction of general relativity. What he actually showed was that singularities are a robust prediction of general relativity. So the Nobel Prize was really for black holes and singularities. So let me start with just a couple of comments about black holes. You don't actually need general relativity to estimate the size of a black hole. Back in 1784, Mitchell pointed out that since the gravitational escape velocity is obtained by setting the kinetic energy, 1/2 mv squared, equal to the gravitational potential energy, if you set the escape velocity equal to the speed of light and solve for r, you get this relation that r is equal to 2gm over c squared. And Mitchell concluded that if you compress a mass m to a size less than this radius, it would appear black because light can't get out. Well, you would expect this simple Newtonian argument to perhaps give you the right order of magnitude or the right scaling with mass for the size of a black hole, but there'd be no reason to expect this factor of 2 to be correct, but in fact it is. This is the exact answer in general relativity for the size of a black hole. The surface of a black hole is known as the event horizon, and the solution in general relativity describing a non-rotating black hole was found by Karl Schwarzschild in 1916, just a few months after Einstein finished his final formulation of general relativity. So this radius, 2gm over c squared, is called the Schwarzschild radius. And for a mass of the sun, this is of order a couple kilometers. It's important to keep in mind that nothing happens when you cross the event horizon. You don't notice it. There's no sign saying point of no return. You keep seeing all the stars around you that you saw before you entered the black hole. Light can still come in, but no signals can come out. Well, classically, no signals come out, But in 1974, Hawking showed that when quantum effects are included, black holes actually radiate an essentially thermal spectrum, so they can be assigned a temperature and an entropy and follow the laws of ordinary thermodynamics. If no matter falls in, black holes will in fact completely evaporate and disappear. So my plan for the rest of this talk is to discuss the relation between black holes and singularities. I'll start with the most common case, which is singularities inside black holes. This is an old story, but there have been some recent developments. Next, I'll talk about some new results which show that certain black holes have singularities on the event horizon, on their surface, not just deep inside. And finally, I'll discuss the possibility that singularities might exist outside black holes. Okay, so we'll start with singularities inside black holes. So what is a singularity? A space-time singularity is a region of space-time where general relativity breaks down due to infinite curvature or infinite gravitational fields. And in 1965, Penrose showed that generic gravitational collapse always produces a space-time singularity. And this usually happens deep inside the black hole. So for a Schwarzschild black hole, which is one that's not rotating and has no electric charge, the singularity is not at the center. It's really in your future. So the picture is shown here on the left. If you're inside a black hole, it's like being inside a cosmology with a big crunch waiting for you in the future. But this is an anisotropic crunch because two directions compress to zero and the third direction stretches infinitely. And so this gives rise to the usual picture of falling into a black hole and being basically torn to bits or shredded by the infinite gravitational tidal forces. And this is the reason people usually say it's not a good idea to fall into a black hole. But real black holes rotate, and the story inside is now different. The solution for a stationary rotating black hole was found by Roy Kerr in 1963. And inside a Kerr black hole, the situation looks like this. The singularity now does look like it's sitting at a particular point in space. It's at something like the center. And you, in fact, don't have to hit it. You can pass right through and go on to another region of the universe. You can't come back to the region of the universe you left behind, but according to the Kerr metric, you can fall into a Kerr black hole and avoid the singularity. In fact, the singularity is actually a ring, and you can go through the center of the ring and enter yet another region of our universe. Even more bizarre is that there are time machines near the singularity of this black hole, and you can travel into your past, or at least your past in this region near the singularity. You can spend as long as you want in this space-time and never grow old. Well, that sounds intriguing. So there was actually some truth to the movie Interstellar. Unfortunately, this region of this rotating black hole interior is unstable. This was first pointed out in 1973 by Simpson and Penrose using a linear analysis showing that some perturbations blow up in the interior of a black hole like this. But over the years, the arguments have gotten stronger. And in 2005, de Fermos studied small but finite deviations from these rotating or charged black holes behave similarly, and indeed showed that the interior is unstable and small perturbations will form a singularity blocking off this entire region and forbidding actual passage through the black hole to other regions of the universe. Okay, that seemed like the end of the story for a while, but recently, it was pointed out that there appeared to be an exception to this uh, explanation that you would always form a singularity, cutting off the space. This singularity, by the way, looks a bit like Schwarzschild singularity, so you really don't have the ability to pass through. The exception is based on two facts. First of all, as I just mentioned, black holes which are charged and not rotating have a similar singularity inside, but don't have time machines. So you don't have that aspect of it, but you still have the possibility, apparently, of passing through the black hole into other regions of the universe. The second fact we need is that the universe is accelerating. Not only is it expanding, but the expansion is speeding up. This is sometimes called dark energy, but the simplest explanation for this acceleration is to modify Einstein's equation by adding something called a cosmological constant, lambda, which is positive. And that will cause an acceleration. Well, it was shown in 2017 that when you have this positive cosmological constant, the interior of a black hole with large charge would in fact be stable. And it's easy to see why this might happen. The earlier instability arose because even though perturbations outside a black hole decay, some of those waves fall into the black hole and they get blue shifted. And the blue shifting, when you fall into the black hole, is greater than the rate of decay of the amplitude outside the black hole. And the waves can build up over time and produce a singularity inside the black hole, which cuts it off from traveling through. But when you have this positive cosmological constant, the region outside the black hole is accelerating apart, causing any perturbations to decay much faster. Well, now they're decaying much faster, and the blue shift is not enough to overcome that. And so you don't get the buildup, and the interior apparently is stable. So this made the possibility that you could actually pass through a black hole of this sort to explore other regions of space-time. But I mean, it's not, we know our universe has positive cosmological constant. We don't expect our universe to have black holes with large charge. If a black hole had an appreciable charge, it would accrete oppositely charged matter and neutralize itself. So this wasn't practical or something we'd expect in our universe, but still theoretically it was very intriguing that there might exist black holes which allow this type of transport through it. However, a few years later, it was shown that if you include quantum effects, you appear to restore the instability of the interior of the black hole. The quantum stress energy tensor, in fact, diverges on a surface inside the black hole, which would then back react, cause another singularity, and prevent any travel through. This was shown in a nice paper in 2020 by Hollins, Wald, and Jean. Okay, so that's the story about singularities inside the black hole. Let me turn to singularities on the surface of black holes. Well, first of all, there's a maximum charge or angular momentum that any black hole of a given mass can carry. And black holes that saturate this bound are called extremal. Extremal black holes have zero Hawking temperature. That means they don't radiate, even when quantum matter is included. They're like the ground states. There's also no force between extremal black holes with no angular momentum and the same sign of the charge. So you can just put black holes of any size, any extremal black holes of any size, as long as the charges are all the same, and the electrostatic repulsion exactly balances the gravitational attraction. And there are exact solutions in general relativity describing this. Now, over the years, since general relativity was discovered, many families of black holes have been found. in the usual four space-time dimensions, three space and time, and the usual Einstein gravity coupled to Maxwell theory. The charged black hole was found by Reisner and Nordstrom just a few years after Einstein discovered general relativity. As I mentioned, the rotating black hole was discovered by Kerr in 1963. And soon after the Kerr solution was discovered, Ted Newman started thinking about how to add charge to the Kerr metric and to write down a solution describing a charged and rotating black hole. Well, by studying various limits, he thought that he sort of narrowed it down to two possible modifications of the Kerr metric, where you could put in factors which depended on the charge and add a charged a Maxwell field to give the black hole some electric charge. But the metric was pretty complicated, and this was long before the era of computers, and Newman didn't want to do all the calculations himself, but he was teaching a graduate general relativity class at the time. So he divided his class into two groups, and gave each group one of his two ansatzes for what he thought the solution might look like, told them to check it. One group came back and said, no, it doesn't satisfy the field equations. The other group came back and said, yes, it does satisfy the field equations. So he wrote a paper and put the entire class on the paper. And that's the paper that was published in 1965. And we still call it the Kerr-Newman black hole, or the charged and rotating solution. Now, people have also thought about black holes in more than four space-time dimensions. The idea that space might have more than three dimensions is very old. It goes back 100 years now to Kaluza and Klein, who noticed that you could unify gravity and electromagnetism by imagining space-time as being five-dimensional, having one more extra spatial dimension. And that idea has carried on to many modern theories of physics, including string theory, etc. Well, the black holes in higher dimensions, the charged black holes that are not rotating, were found by Tangerlini back in 1963, and the rotating black holes were found by Myers and Perry in 1986. All of these solutions have extremal limits, and the extremal limits all have smooth horizons. In other words, they look just like the non-extremal black holes. When you fall in, you don't notice that you've entered the black hole. There's no local signal that you're inside the black hole rather than outside. So after all of these examples, it was widely believed that all extremal black holes have smooth horizons. But we've recently shown that that's completely wrong. Generic extremal black holes have singular horizons. If you're very close to this extremal limit, the black hole will not have a singular horizon, but will have anomalously large curvature much bigger than what you might have expected from the size of the black hole. So basically anything you do to move away from these known exact solutions, I claim will cause an extremal black hole to develop a singular horizon. And so let me describe three different situations which we've explored and found this result. So one of these situations includes something called anti-de Sitter space. So let me say a word about that first. It's hard to confine gravity inside a box. Gravity acts on the walls of the box. And the best box you can imagine is something called anti-de Sitter space. It's the maximally symmetric solution of Einstein's equation with a negative cosmological constant. You can picture anti-de Sitter space as the interior of the cylinder with time running up the cylinder. The boundary of the cylinder is really at infinity. It's infinitely far away in space, but light can reach the boundary in finite time. So that means to evolve any field in anti-de Sitter space, you need to impose boundary conditions. Now, suppose you break spherical symmetry by putting a black hole inside a steel cage or inside anti-de Sitter space with inhomogeneous boundary conditions at infinity. So what do I mean by that? If you think about this boundary at infinity, this time-like cylinder, the usual boundary conditions for, say, a spherical black hole is that your metric on the boundary is a round sphere across time, and your electrostatic potential, this time component of the vector potential, is just constant. Those are the standard boundary conditions, and you get the usual black hole. There's a static charged black hole in anti-de Sitter space. But you don't have to choose these simple boundary conditions. You can make the sphere a little bit distorted and not exactly round, or you can choose your electrostatic potential at infinity not to be exactly constant. And the question is, what happens to the horizon of a black hole if you do that in ADS, or if you just put something like a steel cage in ordinary asymptotically flat solutions without a cosmological constant? For non-extremal black holes, the answer is that the horizon becomes distorted, but remains smooth. There's nothing surprising or unusual that happens. But now suppose you put an extremal black hole inside a steel cage or inside anti-de Sitter with inhomogeneous boundary conditions. For an extremal black hole, the horizon moves infinitely far away in space-like directions. So you might expect that the non-spherical source dies out and doesn't actually affect the horizon, which is infinitely far away in these space-like directions. And if we look at black holes and general relativity without a cosmological constant, that would be correct. The horizon actually is unaffected and remains exactly spherical. But if you add a negative cosmological constant, things are completely different, and the horizon becomes singular in the extremal limit. So the claim is generic non-spherical extremal black holes in anti-de Sitter space are singular. This is a result I found with George Santos and Maciej Kolanowski a few years ago. The metric is actually continuous at the horizon, but not differentiable. And to compute the curvature, you need to take two derivatives of the metric. So the curvature blows up and the horizon is singular. Tidal forces could diverge for ingoing observers. So that's the physical consequence of the singularity. Ingoing observers will experience infinite tidal forces at the horizon, not deep inside. And I want to point out that you don't need to break the spherical symmetry by much. If you put small inhomogeneities on the boundary of anti-de Sitter space and look at large extremal black holes inside, they will have the singularity. Okay, so that was the first example. Let me now describe a totally different situation. I'm now going to set the cosmological constant to 0. So we're talking about ordinary black holes, the Kerr-Newman or Reisner-Nordstrom black holes of general relativity. But I want to add small corrections to general relativity, which come from quantum or stringy effects. We know that in string theory, there are higher derivative corrections to general relativity, and quantum loop effects will also produce higher derivative corrections to general relativity. Now, these come with small coefficients, and they're usually assumed to be totally negligible when describing large macroscopic objects. These small higher derivative corrections are thought to be important only at the Planck scale or very small regions or string scale in string theory. And we treat general relativity as the leading term in a low energy effective action and expect it to give a good description of these large objects. Well, I claim that's not true for extremal black holes. This is work that we've shown over the last couple of years, again with George Santos and Maciej Kolanowski, but also now with Grant Remen. And what we found is that extreme rotating and charged black holes are very sensitive to higher derivative corrections to general relativity. And even small higher derivative terms can cause large extremal black holes to have singular horizons. So in a sense, this effective field theory breaks down because the small higher derivative corrections are producing a large effect on these large macroscopic objects. Okay, that's the second example. And now let me give you one more example. When I was talking about 5-dimensional or higher dimensional black holes a few minutes ago, I mentioned that there was a solution for a charged black hole, which is not rotating. I mentioned that there are solutions for rotating black holes that have no charge. But I never mentioned that black hole which had both rotation and charge. And the reason is that the general solution for a rotating charged black hole in 5-dimensional or any higher dimensional Einstein-Maxwell theory has never been found. We don't know what the analog of this Kerr-Newman solution is in more than 4 space-time dimensions. And that's not for lack of trying. Many people, ever since the Myers-Perry solution was discovered, many people have tried to add charge and have not succeeded. And the question is, why? Well, I don't know why it hasn't been found, but perhaps it's because this general solution of ordinary Einstein-Maxwell theory in higher dimensions has a singular extremal limit. The black holes are only smooth. The extremal limit is only smooth when you set the charge to 0 and the angular momentum to 0. I should mention that in higher dimensions, there's more than one angular momentum parameter. In 5 dimensions, space is 4-dimensional. You have 2 orthogonal planes, and the black hole can rotate in each of these 2 planes. So in 5 space-time dimensions, rotating black holes are characterized by 2 angular momentum parameters, and you have, as I said, smooth solutions, smooth extremal limits if you have both of these angular momentum turned on and no charge, or if you have charge and no angular momentum. But in general, it is singular. Okay, so I've given you 3 different examples of the more general black holes where the extremal limits are all singular. And now let me tell you why this is happening. And there's actually a very simple reason for this. The spatial geometry of an extremal black hole looks like this. So you have a space which is asymptotically flat, or maybe approaches anti-de Sitter space far away. But as I said, in the extremal limit, the horizon recedes infinitely far away, and you have this picture of this infinite throat. You have to go down this very long throat, and the horizon is sitting somehow at the bottom. There is a limiting geometry that you can extract near the horizon. So you can do a scaling procedure, which basically removes this asymptotic part of the solution, focuses on the solution near the horizon, and you get this so-called near horizon geometry, which has enhanced symmetry. Now, even though the horizon is infinitely far away in spatial directions, this extremal black hole can be reached in finite proper time for infalling observers. So it really is part of the space-time. Ingoing light rays, that light rays are null, they have 0 proper time, but there is a natural so-called affine parameter along the light ray, which also remains finite at the surface of an extremal black hole. So extremal black holes should not be thought of as living at infinity. They're very much a part of the space-time, just like non-extremal black holes. Okay, so here's the argument for the singularity. Near the horizon of an extremal black hole, the metric takes the following form. You can approximate the solution by this leading term, which is just the near horizon geometry, which you extract from the geometry right near the horizon. That remains smooth. In all these cases, this near horizon geometry is smooth, but then you get corrections to it, which basically start attaching this the rest of the solution, which is the asymptotic region. And then this correction looks like some other smooth tensor multiplied by a power gamma of this affine distance to the horizon. Now, in all the known exact solutions, this exponent is 1. So when you take derivatives of the metric to compute the curvature, everything is finite, and you get nice smooth horizons, and you get finite curvature at the extremal horizon. But generically, when you do any of the things I've talked about, adding small higher derivative terms, adding small inhomogeneities on the boundary of anti de Sitter, or in 5 dimensions, gamma turns out not to be an integer. And once it's not an integer, and it's less than 2, when you take 2 derivatives, you will find that certain components of the curvature blow up. Okay, so here is actual data from one of these examples. So this is the example of the effect of higher derivative corrections on an extreme black hole in 4 space-time dimensions with no cosmological constant. So the usual asymptotically flat Kerr-Newman black hole modified with some small higher derivative corrections. What I'm plotting here is a log-log plot, and on the vertical axis, this is the difference between the curvature of the effective field theory corrected black hole. So this is the black hole with some higher derivative corrections. You take the difference of that curvature and the usual Kerr-Newman black hole with the same charge and angular momentum. And on the horizontal axis, this is just a radial coordinate y, arranged so that y equals 0 is the horizon and y equals 1 is infinity. And this linear behavior in the log-log plot is showing that this curvature of the EFT-corrected black hole is in fact diverging as you approach the extremal horizon. This data is for a particular case of an extremal black hole with Q over M equal to 0.2, but you get similar results for other choices. You can change the amount of charge on the black hole and the amount of angular momentum. There are actually points for 3 different curves here. There's different colors, but those correspond to 3 different higher derivative corrections. So I should say that the usual action for Einstein-Maxwell, of course, involves a curvature, a scalar curvature term, and then f squared, where f is the Maxwell field. What we're looking at here are corrections of 4 derivatives that come from, say, f to the 4th terms, or terms involving the curvature multiplied by the Maxwell field twice. So those are terms involving 4 derivatives, and there's 3 different ways of writing them. So we have data for each of those. We treat these higher derivative terms perturbatively, so they're independent, and we can look at how the black hole is corrected for each of them. But you see in all cases, the curvature blows up. That was the extremal black hole. What happens if you are slightly non-extremal? So here we're talking about approaching the extremal limit. You can approach the extremal limit in different ways. And here I'm showing data where I've chosen the charge to be equal to the angular momentum divided by the mass. So that's just some line that you can, some way of adjusting the charge and angular momentum as you take the extremal limit. The plot on the left is again a log-log plot. The vertical axis is again the difference in the curvature of the effective field theory corrected black hole, the black hole with the perturbation from the higher derivatives. And the horizontal axis is now the temperature, the Hawking temperature of the black hole multiplied by the charge. You can fix the charge. The charge just sets a scale. So let's fix the charge and think of this as decreasing the temperature. And again, you see this linear behavior on all 3 curves, showing that as you approach the extremal limit, the well, the curvature of the effective field theory black hole is diverging. If you want to know sort of how quickly it diverges, that's shown by this plot on the right, because this is not a log-log plot. This is a regular plot of the same difference of the curvatures multiplied by the temperature, well, times Q. So if you multiply this difference of the curvatures by this temperature, and now take the temperature to 0, you see that they all approach a finite limit at t equal to 0. So the curvature of the effective field theory corrected black hole blows up like 1 over the temperature as you approach the extremal limit, which has 0 Hawking temperature. Okay, well, let me now move on to the last topic, which is the possibility of singularities outside black holes. When Penrose proved his singularity theorem in 1965, he realized that it said nothing about black holes. And he contemplated that there might be singularities that are not inside black holes. They would then be visible to distant observers, and he called them naked singularities. And he then asked whether there was a cosmic censor which would forbid the existence of naked singularities. And so this has become known as a cosmic censorship conjecture, which can be stated as smooth initial data in general relativity cannot evolve to form singularities visible from infinity, these so-called naked singularities. And 50 years later, this conjecture, with a small modification, is still open. Now, there are various approaches to trying to settle this cosmic censorship conjecture. The first is to try to prove mathematical theorems. This is very hard. There are proofs in special cases where you assume a certain amount of symmetry, but that's not enough. Those are very special. To try to prove, we're still far from having anything like a generic proof of cosmic censorship. We don't even have a proof that black holes are stable to small nonlinear perturbations, although mathematicians tell me that they're close to proving that. There were proofs a few years ago that black holes with small rotation are nonlinearly stable, and those proofs ran hundreds and hundreds of pages. So this is a hard business, and I'm not going to say anything more about it. Another approach is to evolve initial data numerically. There's been enormous progress in numerical relativity over the last 20 years or so. There are now many codes which take smooth initial data, sometimes with black holes in various configurations, evolve them, study the merging of black holes, collisions. They're very useful for the interpreting all the data that's coming from the gravitational wave detectors. And so far, no evidence for naked singularities have been found. This is probably the best evidence we have in favor of cosmic censorship so far, is all these numerical solutions. A third option is to look for counterexamples. And that seems like the easiest to me. So that's what I'm going to discuss. And in fact, in the 1990s, a counterexample was found. This was work of Christodoulou and Chaptwick. And what they studied was spherical waves of matter, some spherical scalar field or spherical matter, which is initially incoming in a situation where the matter is coupled to gravity. Now you can assume an initial profile for your spherical wave, have some profile P of R multiplied by some amplitude A. And you can evolve this initial data in general relativity for various choices of this amplitude A. And you know what's going to happen in at least two limits. When A is very small, the field has very little energy. The amplitude is very small, and the matter doesn't curve space very much. You expect it to evolve as it would in flat Minkowski space. the ingoing wave passes through itself, and you end up at late time with outgoing waves. When the amplitude is very large, this initial wave has a lot of energy, and you expect when it collapses down, it's going to form a black hole. But you can continuously vary the amplitude A. And the question was, what happens right at the threshold of forming a black hole? Well, it was shown that you in fact form a naked singularity. There is a critical value of the amplitude where you evolve and you get a singularity which is not hidden inside a black hole. In some sense, you can think of this as a zero mass black hole, or the limit of a black hole as the mass goes to zero, and you get a singularity which is visible to distant observers. Well, you might have stopped at this point and said cosmic censorship is false, but of course people were wondering if if naked singularities could exist in our universe. And for it to exist in our universe, you didn't want any fine-tuning like this required. Now, I should emphasize this is a very modest amount of fine-tuning. There's sort of an infinite dimensional space of possible initial data, parameterized by all of these possible profiles, P of R, and you only have to tune one number for any profile to get the singularity, but nevertheless, it was still something which didn't happen generically. And so people basically redefined cosmic censorship and said that what we really want to know is whether generic, smooth initial data in general relativity can evolve to form naked singularities. Initially, people hoped that this was true so that general relativity would be sufficient to evolve everything outside of black holes. Nowadays, I think many of us hope it's false so that we might possibly directly observe effects of quantum gravity, which is expected at these very small distances or high energies that you might access near a naked singularity. Okay, since cosmic censorship is so difficult, people have considered it in other situations, generalized it away from the initial 4 dimensions and context that was envisioned by Penrose. And you can ask whether cosmic censorship holds in some related environments, such as what happens if space has more than 3 dimensions, and what happens if we add a cosmological constant to general relativity. Well, it turns out black holes are much less constrained in higher dimensions. In 4 space-time dimensions, 3 space and time, black holes are uniquely characterized by just their mass, charge, and angular momentum. There's a uniqueness theorem saying that this Kerr-Newman solution is the only solution. But in higher dimensions, that's not true. There are many black holes with the same, even with the several angular momenta you can define in higher dimensions, there are many black holes that have that mass charge and those angular momenta. Another difference is that black holes in 4 space-time dimensions are always topologically spherical. But in higher dimensions, they don't have to be. There are black holes that have a horizon which looks like a ring. These are known as black rings. And finally, and most importantly for us, black holes don't have to be stable. And in fact, they can be unstable in higher dimensions. So this leads to a breakdown of cosmic censorship. Small perturbations of an unstable black hole cause the horizon to pinch off. And when it does, you generically form a naked singularity. The simplest example is that in 1 extra dimension, so 5 space-time dimensions, there are black strings which have a horizon which is a sphere across a line. So these are basically one-dimensional lines surrounded by an event horizon. And it was shown by Gregory and Laflamme in 1993 that these black strings are unstable. Gregory and Laflamme did a linearized analysis showing that long wavelength perturbations of this black string will grow exponentially in time. And the question was, what does the black string evolve into? Well, that was debated for a while, but finally settled by this wonderful numerical evolution by Louis Lehner and Franz Pretorius in 2010. And what they showed is that the black hole, the black string, wants to break up into spherical, higher dimensional black holes. So let me run this. So you start off seeing a slightly perturbed black string, and you see it quickly form large spherical black holes. These are 5-dimensional spherical black holes surrounded by a thin black string, which itself is unstable, to forming smaller spherical black holes connected by thinner black strings, which are themselves unstable, to forming yet smaller black holes connected, etc. And it's believed that this process will repeat an infinite number of times. You'll go through an infinite number of epochs forming smaller and smaller spherical black holes connected by thinner and thinner black strings. But there's a clock up here, and I'm going to play this again, but what you should notice is that this simulation has been slowed down as we move along, because these epochs happen on faster and faster timescales. The natural timescale is the thickness of the string. And even though we go through an infinite number of epochs, it happens in finite time. So this evolution stops after about 4 epochs of different size spherical black holes. But if I play it again, you'll see initially the time moves very quickly for the initial formation of the spherical black holes. And then I'm slowing down the time to show you that these subsequent epochs occur. And then time is moving really slowly now to get these smaller and smaller black holes. But you can just see the geometric progression and easily convince yourself that the whole thing, if you're sitting at a point on the string which is not forming a spherical black hole, it will indeed pinch off in finite time, producing a naked singularity. Oops, okay, so let's go on. Okay, so that's the higher dimensional story. What if we add a cosmological constant? Well, as I said, if we add a negative cosmological constant, we're talking about solutions which are asymptotic to anti-de Sitter, and these require boundary conditions at infinity. And for reasonable choice of boundary conditions, one can violate the spirit of cosmic censorship generically in just 3 space dimensions. Okay, so now we don't need to add extra dimensions. We're in 3 space, 1 time, 4-dimensional spacetimes with a negative cosmological constant, and you can violate cosmic censorship. I say the spirit of cosmic censorship because what I'm actually going to show you is an example where the curvature grows in time without bound. You don't form a singularity in finite time, but you certainly reach arbitrarily large curvature. So this is work I did with George Santos and Benson Way almost 10 years ago now. We considered gravity coupled to a Maxwell field with a negative cosmological constant. And on the boundary at infinity, we're going to choose our metric to be flat. So this is just 3-dimensional Minkowski space. And the vector potential will again choose to have only a time component. So it's like an electrostatic potential, but it will have a electrostatic potential which is not constant on the boundary, but varies with this radius. And we're going to assume that this mu of r, again, has some profile, f of r, which goes to 0 at large distance on the boundary, but is non-zero near the origin. We're assuming everything is axisymmetric. And we're going to give it some profile, which I'm now calling little a. Some amplitude, which I'm now calling little a. And we look for static axisymmetric solutions with these boundary conditions. And these solutions describe static self-gravitating electric fields. And what you can show is that smooth solutions exist only for the amplitude up to some finite maximum. The solutions look roughly like this. So this is the electrostatic potential we are imposing on the boundary. It's not constant, goes to 0 at infinity. This induces an electric charge density on the boundary, which is positive near the axis and negative far away from the axis. And roughly speaking, the electric field lines in the bulk look something like this. Okay, so now what you can do is to make the amplitude time dependent. So we let the amplitude depend on t. You start with initially a equals 0, so you have just pure anti-de Sitter space, and slowly increase it to an amplitude bigger than this maximum. Well, when you're slowly increasing it, you expect the solution to be close to these static solutions we have found. So in some adiabatic limit, the solution will follow the static solutions. But once the amplitude gets bigger than A max, there is no static solution for it to approximate. The bulk can't settle down to any smooth solution, and we expect the curvature to grow without bound, violating cosmic censorship. And that, in fact, was confirmed by a full time-dependent numerical relativity calculation just shortly afterwards by George Santos and Toby Crisford in 2017. Okay, a few comments. The blow-up of the curvature is not just on the axis, but over some large region. So it's a large, you get large regions of curvature. The singularity, as I said, doesn't form in finite time, but it clearly violates the spirit of cosmic censorship. And this violation is stronger than seen in higher dimensions, because in higher dimensions, when the black hole pinches off, it really is just a small region of the space-time where the curvature becomes very large. Okay, I think I'm out of time, so let me summarize. So in the first part of the talk, I showed you that in principle, one can travel through black holes to other regions of the universe, but in practice, it's probably forbidden because of this instability forming on a surface inside the event horizon. I then showed you that generic extremal black holes have singular event horizons, unlike all the known exact solutions that have been studied. And finally, we saw that naked singularities are common in more than 4 space-time dimensions, or in 4 space-time dimensions with negative cosmological constant, and might even occur in 4 dimensions with 0 cosmological constant. And I'll stop there. Thank you.
Okay, thank you. Thank you very much, Gary, for very good talk. And I think it's time for questions and discussions. So if you have any questions, please raise your hand or just unmute.
Sorry, can I ask a question? So, yeah, thank you very much for very beautiful talk. It's quite stimulating. And I have a question about one question is about ADS safety. So in this obvious question, but you have this naked singularity in ADS, depending on this construction using gauge field in the
Right.
and that gets means if we have some singularity, so we have to go beyond classical gravity dual. Maybe we need to take into account stringy correction. Or my question is that how can we see this in kind of conformal field theory picture? Maybe in conformal field theory picture, we cannot capture that kind of singularity in terms of some universal dynamics, like very chaotic dynamics. If we have a chaotic dynamics, it looks like Einstein gravity, but maybe we have some unusual non-equivalent process which cannot be captured by classical gravity dual.
Okay, let me first say something which I know, maybe not exactly what you're asking, but if we go back to the extremal black holes in ADS, so I showed you that the non-spherical extremal black holes in ADS have these singularities on the horizon. And you might say, how do we see that from the dual field theory? I mean, what's the signal of that from the field theory? And we thought thought about that. And at first I thought that was a very hard problem because I thought we would have to model infalling observers and then think about, what's the signal of tidal forces in terms of the gauge theory. But it turns out there's a very simple signal of this. These tidal force singularities modify black hole thermodynamics. So it turns out that in many cases, the entropy, the way the entropy depends on temperature away from extremality is modified. It's not the usual linear growth of temperature. It grows with a power of temperature which is less than 1. And so that means that if you were just to put take your strongly coupled field theory and put it on some inhomogeneous space or put some inhomogeneous source and study the thermodynamics of the system near, well, in the analog of this near extremality, you should see some anomalous behavior or some modified thermodynamic behavior. Okay, so that's one signal that's sort of easy to see. But I think, were you asking about this last example of this?
Or maybe in that case, maybe so. Is it correspond some? Can we understand it? Some non-equilibrium dynamics of some quantum many body system. This anomalous behavior.
Can you understand this anomalous
Yes,
thermodynamic
yes, from
behavior?
some CFT or some non-equilibrium dynamics.
Yeah, so I mean, in fact, there is an explanation in terms of some SYK model. So it was originally shown that the SYK model will reproduce linear temperature growth away from extremality. But it was also pointed out that if you have some low dimension operator added to that theory, then it dominates over the SYK mode and you don't
I see.
So that's really what we're doing. With these perturbations effectively turn on these low dimension operators. It's this low, the lowest modes which are unstable. Yeah.
Maybe the operator have some anomalous dimension. Maybe that changes. I see. That's the reason. I mean, you might expect this kind of singular thermodynamics.
Right.
I see. Yeah, that's my question.
Very good.
Thank you very much.
Okay. Any other questions? I have a question actually. So when you discuss the singularity at the horizon of the extremal black hole, you divide your extremal black metric into near horizon geometry plus perturbation multiplied by a fine distance with certain power gamma.
Okay. Yeah.
Yes, but even for the non-extremal black hole, because the affine distance to the horizon is finite, and maybe we can approximate horizon as a linear spacetime. Then again, we can divide the metric into some linear spacetime plus affine distance times power, some certain power. But somehow, only for extremal case, you have a non-integer power. That's called a singular structure.
Yeah, I think what's important is that this near horizon geometry has this ADS2 factor, right? The enhanced symmetry includes the dilations. And so you have the scaling symmetry in rho. Well, we're basically looking at modes. Yeah, I think that the what's a good argument? Well, I mean, having this infinite throat, it gives you, I think, more separation of the near horizon geometry, and the corrections, the perturbations go to zero. For a non-extreme black hole, let's see, the perturbations, let's say maybe they don't vanish fast enough or something in a Rindler approximation. Yeah, well, I'm not sure offhand exactly, but I think it must be related to not having this dilation symmetry that is important.
Okay, thank you. Any other questions? Okay, then it's good time to stop just here. And okay, thank you very much, Gary, for a wonderful talk. Thank you very much.
Thank you.
Thank you.